Okay, so now we're recording. So, centrifugal stations and sugars. The first thing to know about centrifugal stations and sugars is that there are two different types of stations that you can utilize. And if you look at here we're looking at the sugar stencils over here on the left. And you go to the separator/centrifugal shaped stencil. There are 6 stations in that stencil, and 3 of them are centrifugal shapes. But you'll notice that 2 of them, this one here, the 2 output batch and the 2 output continuous centrifugal, they have 2 different shapes. One looks like a batch machine and the other one looks like a continuous machine. However, those are the same calculation. So those actually refer to the same sugars station in the background. They're just 2 different physical drawings of that station. Now, why do we do that? Well, because sugars is a continuous steady state mass and energy balance program. The batch centrifugal and the continuous centrifugal, if they only have 2 outputs, they're modeled the same. And when I say 2 outputs, I mean a centrifugal that has only a sugar output and a syrup runoff, or a green output, or molasses, if you want to look at it that way. The other type of centrifugal station is the 3 output batch centrifugal. And the 3 output batch, of course, is really only drawn as a batch centrifugal because typically only batch machines have 3 outputs. So now we're talking about a machine that has not only sugar and the green syrup runoff, but also what some of us would call a high wash, or just a wash runoff. And that's what we're looking at here in this example. This is the beet sugar end example, and I've added just a couple of labels to it here. But this station 3020 is to represent a white centrifugal. And as you can see, I'll zoom out just a little and then scroll. So we have a white pan here. And in the USA, we call it fill mass. In sugars and maybe around the rest of the world, it's called masaquit. Is this crystal and syrup suspension that comes out of the white pan. That's fed to the centrifugal. And then we have wash water fed to the centrifugal as well for the sprays. And then the outputs from the centrifugal are the sugar, of course, coming out the bottom. The green syrup runoff, that's on the right side here. And the high wash, or the wash syrup runoff, on the left here. So today we're going to talk in most detail about the 3 output batch centrifugal station, because if you can model a 3 output batch centrifugal, you'll have no problem modeling a 2 output continuous or batch centrifugal. It's the same process, it's just simpler and easier. So we'll focus on the more complicated one here so you get all the information, and that'll prepare you for either one. So now that we've talked about that, one thing that is really key in understanding how to model white centrifugals, or any centrifugals and sugars, is to keep in mind the fact that sugars relies on an evaluation of an actual centrifugal performance in order to set up the calculations to model a centrifugal station. Because if you think about a centrifugal, it's a very complex mechanical process where you have the crystal size, the size of the slots in the screen, the speed and acceleration of the basket. All of these parameters play into the performance of the centrifugal. And in order to do a rigorous first principles model of that, you'd need some very high or very complex mechanical force and mass modeling software, which sugars is not. So what it does instead is take results from an actual operating centrifugal, you enter those, it evaluates that centrifugal, and then it creates some performance indexes based on those parameters, and then uses those performance indexes to model the centrifugal within the rest of your overall process model in sugars. So we'll go through how to do that here. The first thing we'll do is go ahead and open up the white centrifugal dialog box. And you'll notice the first thing that comes up is actually the 3-output centrifugal evaluation. So this right here, this dialog box is not necessarily setting any parameters for the centrifugal. What it's doing is it's asking you to enter data from an actual centrifugal that you're wanting to model. Okay, so we have to start with the mass quit coming to the centrifugal. And of course, in this model, that's a flow stream that's already defined. So all the parameters from that flow stream are shown here. But we have to tell it in the process, in the actual centrifugal, what's the flow of that mass quit. And you can do it in volume units, as are currently set up here, cubic meters per hour, or you can switch to weight units if you know the weight of the mass quit flow to the centrifugal. So either way is fine, and sugars will convert between the two as you switch. See the number changes there. So you have to enter the mass flow or the volume flow of the mass quit coming to the centrifugal. Then you have to come to this box here called wash, and you have to enter the parameters of the water or syrup or steam that's being used to wash the sugar. So that would be this stream coming in the side here, input port number 1. If you're using syrup wash, then you need to enter the dry substance impurity of the syrup you're using to wash. If there's any steam present in the water, then you would need to enter the quality of that wash, so quality being % steam. And then you, of course, need to enter the temperature of the wash and the flow of the wash. And one thing to keep in mind when you're modeling a batch centrifugal is that this flow is the average flow over the entire centrifugal cycle, and that includes pre-flush and any wash cycles that you have. So you don't want to just read a flow meter for the 10 seconds or 20 seconds that the wash is running and assume that that's the flow to enter here. What you need to do is read that flow, but then divide the total flow during the wash cycle over the entire centrifugal cycle time. That's the flow you need to enter here, the steady state overall average flow. And then the next section is the flows out of the centrifugal. So, of course, in this case, this is a 3-output centrifugal. So we have a green flow. That would be your molasses runoff, green runoff flow. You need to know the dry substance, the purity, and the temperature. And this data is going to come from lab analysis of the centrifugal actually running in the factory. So you would go take a sample or maybe a series of samples and then enter that data here. And the temperature, of course, you'll have to measure. The wash, now this wash is not the same wash as the wash that you're using on the spray bar. This is what I would call high wash, but in other places we call it wash syrup. This is after the syrup separator switches, you get this material as a runoff, and typically it's toward the end of the cycle, and it's a much higher purity stream, lower color, and you recycle it back, which is what's happening in this example model. It gets recycled back to be crystallized. Again, you're going to take lab analysis data of the dry substance impurity, enter it here, and the temperature as well. And last but not least, of course, sugar itself. Remember, this is wet sugar coming directly from the centrifugal, has not been through a dryer yet, so it's going to have a dry substance, a little bit lower based on the moisture that's still contained in it, and the sugar purity. And this being a white centrifugal, the sugar purity is very high, but if this were a lower purity centrifugal station, that sugar purity can drop quite a bit depending on the application. And the temperature as well. So again, lab analysis data and then the measured temperature. So you'll enter all this information, and this is just to define the conditions and the performance of the centrifugal that you're trying to model. Now you're going to say, well, what if I'm modeling a new centrifugal? I haven't installed it yet. I don't have this data. Well, in that case, you're going to either have to make some assumptions or rely on the centrifugal manufacturer that you're planning on purchasing from to give you the expected performance data. So they should have predicted values for all of these to be able to enter here to get that centrifugal evaluation.
Hey, Scott,
before I move on. Yeah, perfect. I was going to ask for questions.
Yeah. So on on the white machine, if you have a syrup, say you have a syrup wash initially, and then you have a wash water step after that. Say your syrup wash was 6 seconds, you spun it a little bit, and then you added a wash water, all in the same thing, all in the same batch. And the syrup doesn't really have a wash. That goes right to the high green, whereas when you start the wash water, you can separate it, and based on, you know, process conditions that you've measured. I've done that. So I really had 2 white centrifugals in series, and one was a syrup washer and the other one was water. Can you do it all with one now, or I'm a little goofed up there? I don't understand how it would work if you...
Yeah, to do that, there's 2 ways you can deal with that. I think the way that you mentioned is probably a pretty good way to do it. Actually, put in 2 centrifugals in series. You could just use a 2 output centrifugal for each of those, because I'm assuming that your syrup separator is never overlapping that first syrup wash. So all the syrup wash goes to green, and then all the water wash goes to wash. If that's the case, then 2 centrifugals in series makes a lot of sense. The only other way I could see to do it, if you think those washes might overlap some, is to do just a mass weighted average on the dry substance impurity of the wash that you enter here in this evaluation. So these values right here, you could just say, well, of the total between the water and the syrup, if I put it all together in the same bucket, what would my dry substance impurity be, and what would my total flow be? And then sugars can still calculate the performance indexes based on that data if you look at the total, you know, the overall outputs. But it may not be quite as instructive or quite as easy to manipulate as the 2 in series. Does that make sense?
Yeah, it does. I have another question. On the Massic, can you click the Massiquite tab? The button up there? There you go.
Yeah.
Now.
Yeah, so that, go ahead.
So this thing too, it always helps to know what this is as well, because that sets your target on the next page. And when you start messing around with the green purity and the sugar and all that stuff, it has to coincide with what you're saying your Massiquite is here. So I guess do most people just get that strainer and actually strain out the crystals to get their Massiquite purity, or do you assume a super saturation and try target that? Or I guess what's the rule of thumb on this thing? Because it has an impact on what green you can use when you're actually trying to balance the centrifugal station. So
yeah, so I'm glad you brought this up. We definitely wanted to look at this. So this Massiquite evaluation here is where, first of all, if you think there's any changes in solubility, any reason to use a different set of solubility coefficients than you've been using throughout the model, you can change those here by selecting either a set of the given ones in sugars or by manually overriding them here. Not typically necessary, but just be aware it's available. And then you'll go ahead and enter the Massiquite parameters from the process. So this again is lab data from the actual factory. These do not have to match the values that are coming in the sugars model right here, because you might be modeling a different scenario. But you want the values that are actually defining are actually being fed to the real centrifugal that you're evaluating here. And then also, if you know the supersaturation coefficient of that Massiquite, you can enter it here. But if you don't, you can click calculate and enter the parameters of the mother liquor. And this is where what Jeff's talking about comes in. If you have, we call it a Nooch press or a Filmas press. Basically, it's just a little device that uses air pressure to squeeze fill mass and push a sample of mother liquor out. And they're not as easy to use as you might think. You have to make sure they're warm so that you don't get more crystallization occurring whenever it happens. And but if you have one of those and you can run that test, you can take lab analysis of the actual mother liquor in the fill mass and enter that data here, and then sugars will calculate the supersaturation coefficient for you. So either way works. And then once you have all that information here, just for curiosity's sake, you can click calculate parameters, and it will calculate the density, the non-supercritical water, the percent crystals, and the mother liquor parameters here, just so you can view them. So does that answer your question, Jeff?
Yes, and that's probably the most accurate way of having a representative centrifugal station, is if you could do that a couple times on your process and get those numbers and feel confident that your mother liquor purity that you have on your centrifugal station is representative of actual factory performance then, right? Does that sound correct? Or?
Yeah, definitely the best way to do it is if you have that fill mass press and you can get a sample of mother liquor coming out of the pan, so you know exactly what you're feeding the centrifugal. Okay, so I think we've covered the evaluation. So the next thing that you need to do is when you click OK, normally when we click OK, we expect a dialog box to go away. But in this case, it actually comes to the next in the series of the process for for three-output centrifugal modeling. And what it's showing here is the results of the evaluation. So this is what sugars calculated based on the data that we gave it from an actual centrifugal in a factory. And you can see there's some data from the mass quit, the wash ratio. So this is the percent mass wash water or syrup added to mass quit ratio, and the heat loss in the centrifugal. And those are all just calculated based on the information that we gave it. But these three parameters right here are actually more, I call them the performance indexes that sugars will use to model this centrifugal once you finish this setup here and balance the model. So the first one is the crystal loss ratio. And the crystal loss ratio is simply the mass of sugar crystals that came in with Massaquit that are lost to either the green or the wash runoff flows out. So in this case, we're looking at almost 21% of the crystal mass that came into the centrifugal is dissolved and passed through the screen with one of the runoff streams. And that, of course, is a pretty important parameter because that drives directly to your yield. The next one is the liquor purge ratio. Again, we're talking about the mass, and this time in liquor instead of crystals, but it's the mass that passes through the screen and ends up in one of the runoff flows, either one. So when we say liquor, we're talking mother liquor. So for a white centrifugal like this, we want to see a very high number. Really, for any centrifugal, it should be a pretty high number, but in this case, it's very high because the inverse of this, so if we took on 100 minus this number, that would be what liquor is left on the sugar crystals after they leave the centrifugal. So we want that to be very low. And the last number here is the wash purge ratio. Same concept, but now we're talking about the wash flow in this case, it's only water, but it could be a syrup wash. How much of that is passed through the centrifugal screen and leaves with one of the runoff streams? And in this case, or in these three ratios, we don't differentiate between the green runoff and the wash runoff in a three-output centrifugal. That's later here in a minute. But these are just determining how much of each input fraction goes out through the screen to one of the runoff streams. And I'll come back to this little checkbox for use purge data in just a minute. The next box here is the green flow to wash flow split. And this is, of course, is specific to a 3-output centrifugal. Now we're specifying of those things that we were talking about up here, how much of each of those losses or how much of each of those things passing through the screen go to each of the 2 runoffs. So it's green divided by wash. So in this case, we're saying that 69% of the crystal loss goes to the green runoff stream. 97% of the mother liquor goes to the green runoff, which makes sense because the green runoff is typically high color, low purity. The wash runoff should be very high purity and low color, so we don't want very much of the mother liquor going with the wash. And how much of the wash flow in goes with each stream? In this case, 80% goes to green. And then this box in the middle here, it just gives the overall mass ratio of green to wash runoff flow. So in this case, over 90% of the runoff is green, so we have a fairly low wash flow in the runoff. As you'll notice, all of these parameters are in blue boxes, which in sugars means that you can modify them. So if for some reason you don't like these ratios, or if for some reason you decided you didn't want to do the centrifugal evaluation, you know all these ratios and you want to just enter them yourself, you can certainly do that. The danger, of course, is that if these are not entered in a mass balanced combination, the model may not balance and the centrifugal may not be able to be balanced. Sugars automatically calculates them all in a balanced combination based on the inputs that you gave during the evaluation. So as they are right now, we know they'll work. But if you start modifying them, just be aware that if they're not balanced, it may cause a situation that's not feasible. And so the last box here is the sugar flow out. This gives just the information based on all the calculations for how much of the input crystals go with the sugar out. Of course, that should be a high number. How much of the mother liquor goes to the sugar out, and again, in a white centrifugal, we want this to be a very low number. And how much of the wash flow in goes with the sugar output. In this case, since the wash flow is only water, this would just be related to the moisture of the sugar coming out of the centrifugal. So now we get to these 2 pink check boxes, and if you notice, it's one or the other. You check one and the other one's unchecked. And essentially what this is a way to specify how sugars should sort of control the centrifugal during the balance calculations. And it will affect the results. One way is, and this is the default, is to use residual data for iterations. So what that does is it tries to hold the residual mother liquor on the crystals in the sugar constant as it balances the model. So in other words, if you keep this box checked, sugars is going to try to hold the sugar quality constant and adjust the wash flow and the green and wash ratios and all of those things in order to maintain that sugar quality as it balances. So that's one way that you may want to balance the model. It just depends on your goals. The other way, if you check it up here, it says use purge data for iterations. This is going to maintain all of these purge ratios in the centrifugal, and sugars is going to allow the sugar quality, the residual mother liquor on the sugar and the moisture and all of that to adjust based on the input conditions. So if you wanted to just basically make a change to the mass quit coming to the centrifugal and see what the impact on sugar quality might be, then you would want to check this use purge data for iterations box so that you can see what happens when those changes occur, and assuming no other changes have happened in the centrifugal. So assuming that your wash ratio and your green and wash runoff ratios are all the same. In other words, no operator intervention or anything like that. Any questions about that? That's kind of a key piece right there.
What's the default, Scott? I mean, I
The
never
default
really
is,
mess with those that much. So which one does it? And I don't really look at that page that well either. I just know what's going in and I know what's coming out, and I just let it do it so it matches what the actual is. Is that the right or wrong way to do it, or do you have to pick these every time, or what?
no, honestly, Jeff, I think you're on the right track. I would, if you have good data from a centrifugal that you're modeling, you definitely want to just leave all of these ratios alone, because they've been calculated based on that data, and that's the best thing you've got. Then it just comes to these two check marks. Which one you want to do depends on what the goal of the model is. If you want to, like I said, if you want to see the same basic sugar quality all the time, which is, that's what the factory typically does. It adjusts. You have a centrifugal operator adjusting centrifugal operating parameters to maintain sugar quality. So if that's what you want the model to do, you would keep this use residual data for iterations box checked. And I believe that is the default setting. But if for some reason you were trying to evaluate what's the impact of changes in the factory on sugar quality without adjusting the centrifugal parameters, you'd switch over and use this purge data for iterations box.
Okay, thank you.
Okay, so once we've completed all that, Sugars calculates some more information for us. Again, this is just sort of FYI down here in this box, giving me the weight percent of each output flow, and how much crystals from the massiquit go into and how much are melted in each stream, supersaturation and heat losses. And then, of course, the big, most important parameters are these crystal loss and percent non-sugars in the sugar. Crystal loss is the same as up here in the crystal loss ratio, and the percent non-sugars is basically very similar to this mother liquor and the sugar flow out, but it specifies the dry non-sugars only. And once we're done with all that, we can click OK, and now the centrifugal is all set, and we can balance our model with the inputs and outputs that we've given it. Now, I've shown this example here just to show it in context in a full model, but I think what we'll do now is just go through and build a very simple 3-output centrifugal from scratch. So you can see the process. I have some example parameters to enter as we go through it. So I'm going to go ahead and close out of this model. And then I'm going to open a blank model I had ready to go. And we'll go through it step by step so you can see how an example works. Okay, so we have to go to the separator and centrifugal shapes, and we're going to choose a 3-output batch centrifugal. Drop it on the model. And I'll make it station number 1000. And then we'll zoom in so we might actually see it. One thing that happens immediately when you open a new centrifugal dialog box is it explains exactly what I discussed earlier about using actual centrifugal data to set up the performance of the centrifugal. So once I click OK on that, I come to the massiquit evaluation that we discussed earlier. So we're going to select typical cane values for solubility, because I don't have, I haven't set up solubility coefficients in this model yet, so I had to do that first. Dry substance is going to be I don't have a dry substance of the, oh, there we go, 91.7. Sorry, just had to find it in my notes. Total purity 93, and temperature 76. And I don't know offhand what the supersaturation coefficient is, so I'm going to enter some mother liquor data to calculate it. So mother liquor in this case is 82%, purity 83.8%. So if I click OK, now I get a supersaturation of 1.43, which is a pretty high number. This is all just fake data here, so we may get some interesting results. So when I click OK, it comes back to the evaluation. I do need to give this centrifugal a name. So I'm just going to give it a name there. And now we need to list all of these input parameters. So I'm going to go into weight units, 100 tons per hour. And we're going to use water only for the wash. And I have that data in volume, so I switch back to volume units, 100 liters per minute. And temperature, we'll say it's 100 degrees C. So it's a saturated water flow. And okay, so the green out, we have measured at 76.6 dry solids, 85 purity, and 72 degrees C. And again, this would all be lab data that we've taken from the factory. Wash out, 73.4 dry solids, 95 purity, and 71.2 degrees C. And the sugar, 98.4 dry substance, 99.95 purity, and 67 degrees C. So this is a water-only washing centrifugal. I've given it the mass quit flow, which I'm seeing in my notes is actually supposed to be 50 cubic meters per hour. So sorry about that. The wash flow was 100 liters per minute. And again, that's the average flow over the entire centrifugal cycle if this is a batch centrifugal. So we have to take the flow during the wash portion of the cycle and then divide that by the total time of the cycle. And then all of the lab data from the green, the high wash, and the sugar gets entered down here. Click OK, and now we have the performance calculations. So we get the crystal loss ratio, liquor purge ratio, wash purge ratio, and all of the green to wash split ratios calculated based on that data. So in this case, we get a 17.4% crystal loss and a 0.34% of non-sugars in the sugar. So it looks like in this case, compared to the other one, we're maybe washing a little less. Our yield is a little higher, but our sugar purity is a little lower. And for now, I'm going to leave the box checked here for use residual data for iterations. Okay. Now I have my centrifugal station, but I need to give it all of its input and output flows. So I'm going to start with a connector for mass quit going in. And let's put it on the product layer. Now, if I open that dialog box, this is an input, an external input flow, so I have to give it a name. And then I have parameters for flow. I'm just entering based on my notes. Of course, this would be based on your own modeling, or if it was part of a larger model, then this would be calculated by sugars coming from a pan. I'm going to use the DS impurity entry for the liquid portion, so this would be the mother liquor, 82% DS and 83.8 purity, and then we've got 52.5% crystals, color are 2500. I do need to select those solubility coefficients again, so I'm going to use that as Kane values. And just for a check, I'm going to go to parameters here. Okay, so I made some sort of mistake. Okay, I know what I did wrong. Oh, wow. So that killed it completely, but we'll get it back. We'll just delete that one. What I did wrong is I didn't enter the sugar content before I calculated the DS impurity. So we're going to fix that this time. Okay, we're going to have to start over. Sugars doesn't like it when the components don't equal 100%. And that's what I did wrong, is I entered the DS impurity and as if the stream was 100% liquid, and then I entered sugar content, crystal content after that, which increased the total to 152%, which is not okay in sugars. We have to have our components add up to 100%. So we're going to start over here and do it right. So that's 1,000. Okay, so this was 1.7. This will only take a few seconds. 3, 6. Solubility coefficients, of course. And then that's 82. 3.8. Okay. Okay. White centrifugal. 50. Wash. Oh, this is wash. 100 degrees C, flow 100 liters per minute. Green. 76.6. B5. 72. 3.4. 95. 1.2. 98.4. 9.95. 67. Okay. Okay. All right. Back to where we were. Nectar. Okay. Aspirate 1,000 kilograms per hour at 76 degrees C. Now enter the sucrose crystals first, which were 52.5. Then go to my DS impurity for the mother liquor, which is 82 and 83.8. Now my total component fractions will add up to 100 because it knew that the liquids portion of the stream was only what's left over after the solids. That's just something to keep in mind. If you're using the DS impurity entry to calculate your liquid stream components, make sure you've entered all the solid components first, or come back and redo this before you click OK on the stream. So we're going to select our solubility coefficients again, and our color was 2500. Okay, much better. So I'm going to go ahead and add a flow legend so we can see a little bit of that data. Color, DS crystals, right there. So that's our mass quit coming to the centrifugal. We also need to give it some wash water. And I want to add that to the water and condensate layer. By the way, if you've never used these layers here, there are a list of them automatically added when you start a sugars model. And they're set up with colors and things that match what those are labeled. So water and condensate is blue, steam is red. And you can adjust that if you like, but it's just a convenient way to get the colors what you want them to be for different types of streams and sugars. All I have to do for this stream is give it a name, a temperature, and a component fraction listing here. We don't have to tell it how much because sugars always calculates the wash water to a centrifugal as a required flow. So we'll leave that 0 and sugars will calculate that when we balance. Let's see, it looks like, oops, I may need to, yeah, because of the pressure, I need to set this at 99.9 to keep my total, because what it did was it saw that it was 100 degrees C at atmospheric pressure, and it assumed that all that water needed to flash to vapor. So we want to keep it water, so I'm going to keep it just under saturation there. Okay, and we'll add a flow legend, weight, pressure, yeah, temperature. Now we have 3 outputs that we need to add to the process. One being sugar coming out, and I'm just going to copy that, copy and paste this other stream because sugars is going to calculate everything for this, so we don't have to enter any information at all. I will put a flow legend on it so we can see weight, temperature, yes, purity in crystals, and let's also put the green runoff. Control G. So I just pasted another one of those streams on there. Once you have a stream that's on the correct layer, and for output flows, you can just copy and paste it. Makes it a little faster. So this is our green runoff. I'm going to add a flow legend for it as well. Temperature. And we have our wash runoff over here. So again, I'm just pasting a copy of that stream on there. And we don't have to specify anything because sugar's going to calculate everything for those output streams from the station. Weight, temperature, purity. Okay, so now we have specified the centrifugal based on actual operating data from the factory. We've given it mass flow coming to it. We've given it the wash water coming to it, and we didn't have to say how much because sugars is going to back calculate that. But we did tell it that it's all 100% water at 99.9 degrees C. And all of these other flows are going to get recalculated based on the centrifugal. So I'm going to come up here and go ahead and balance the model. And there we have it. So with a 100,000 kilogram per hour mass foot flow with the parameters we input, we're going to yield 44,200 kilograms per hour of sugar. It's at 98.4% solid, so it's got 1.6% moisture, 99.95 purity like we specified, and 93% crystals based on the total.
Hey Scott, would you add color to the output sugar in the wash color so we can see what those are?
Absolutely, good idea. Yep.
Thank you.
Color and color. Yeah, so as you can see, because color is considered in sugars just basically another stream component, and it's treated similar to non-sugars. So you can see that the green flow takes the majority of the color, and the wash flow has a much lower color because it's a higher purity, and the sugar color itself is even lower yet. So one thing I wanted to demonstrate here is the difference between the ways that sugars adjusts the centrifugal during the balance. So every time you reopen the centrifugal dialog box, you get this evaluation. But if nothing's changed, you just click OK, and you get to the performance calculations dialog box. And this is where we can switch between residual and purge data for iterations. So I'm not going to change it right now. I just wanted to point those out, because what we'll do here is let's change the conditions of the match quit coming to the centrifugal. So let's say that the mother liquor is at a little bit lower purity. So instead of 83.8, it's 82.5. Okay, so they automatically recalculated the water, sucrose, and non-sucrose components. All right, so right now we're using residual data for iterations. So Sugars is going to do its best to balance this centrifugal and maintain the same sugar quality output. So I'll go ahead and click full balance. And you notice that the sugar parameters didn't really change much. The only things that changed a lot were the wash and the green and washes output. But if we come back into the centrifugal and we switch to use purge data for iterations and balance. Now, I don't know if you noticed, it's a pretty subtle change, but the sugar parameters did change some. So in this case, it's utilizing the original wash ratios and green and high wash ratios that came from the factory data, as if no one's adjusting this centrifugal. We're just leaving it alone, and we're letting whatever changes in the match quit occur affect the sugar by whatever effect they may have. Does that make sense? Is everyone clear on that? Okay. Well, we're at we're about 45 minutes now, so that's it's good, because I'm just about finished. I'll open it up to any general questions about centrifugal stations or anything else that anyone has to ask.
I have a question again, Scott. So say somebody asks you from production, they wanna run a 2500 color high wash color back to the melter station. How would you adjust that now? Would you go adjust your high wash purity to get that 2500, or what would you do?
The first thing I would look at is right here at this green to wash split, because basically, I mean, I think the way you would achieve that on your centrifugal itself is by adjusting the syrup separator. At least that's what I would do if I were running the centrifugal. So the syrup separator is basically right here in this green to wash split. So I would send more in this case, because you can't see it behind the other dialog box there, but our color was only, I think, 1700 in the high wash here in this case. So if we're trying to raise it to 2500, I would reduce this green percentage, which would raise the amount sent to high wash, which would raise the amount of color and non-sugars sent to high wash.
I never do it that way. I just adjust the wash purity, and I usually adjust it to get my color, and it seems like it calculates that way. Is that wrong then, or what?
You're going back to the evaluation here?
Yeah, right there in the middle. Your 95 purity, so lower that to 94.5. Just change that number.
Yeah, and that will work, Jeff, but what it means, though, is that probably if that occurred, there would be some changes to this green purity and possibly even the sugar. And so ideally you would have some lab data for all of these that match from that situation.
Yeah,
does that make sense? If you just
I kind of get into an iterative pattern there to get all those to match, and those are the ones I adjust to get the color profile right and the purity right. And because I don't know what those other numbers are. They're a little bit more, yeah, see, there you're getting closer. So I'd go a little bit more and let it calculate whatever it needs to calculate for purity, because sometimes they don't measure the purity. It just ends up being a color there. But I don't know, is that all goofy then or what?
Well, essentially what you're doing is you're extrapolating from actual performance data out to some condition that you maybe never measured in the factory, or I mean, it sounds like it's a condition that occurs, but they just don't have good data for it, and that's a challenge that people run into all the time in modeling centrifugals. Is, you know, I want to know what happens if I do something that I've never done before. So what you're doing is probably, like I said, either that or just going directly to that green to wash flow ratio and just trying to see if you can increase the amount of syrup separated to the high wash. That may work too. But again, because sugar centrifugal stations are modeled based on actual data from a centrifugal evaluation, then it does get a little tricky if you're trying to extrapolate to some data point that you don't have actual operating data for. But it can be done, and I think what you're doing is probably one of the best ways to do it. There's usually, of course, multiple ways to do almost anything in sugars modeling.
Okay, because it seems like factories are very conscious of the color profile throughout all these things. So if they do regularly take colors of either high green, high wash, and sugar color, they always have, because that's a quality thing. You can kind of adjust those things to match all of those colors, and then when I do that and I get the high green color of the factory, the high wash color of the factory, and the sugar quality is what they actually got for a day or a week or whatever, then I feel confident that my machine is kind of set right. Is that okay? Or
yeah, as long as as long as the color profile and the purity profiles are relatively matched.
Yeah.
You'd want to be careful that you don't. I mean, you might match up all the colors to the factory, but then find out that for some reason the non-sugars passing through are much higher or lower than what's really there, and that of course will throw everything off.
Yeah, I use the purity the same way as I use the color. It all should match when you're done with it. So.
Yeah. So yeah, that once you've got that, you've got an accurate model.
Okay. Thank you.
Okay, well, if there aren't any other questions, I'll go ahead and wrap up. I appreciate everyone joining us. I apologize again for the technical difficulties we had the first go round, but everything seems to be working well today, and I'm glad that some of you were able to join. I did record this whole session, and we will make this recording available on our YouTube channel, and we'll send out that link to everyone that registered after I get it uploaded. So thanks again. Appreciate everyone being Sugars users, and we'll let you guys know in a month or two when we schedule the next webinar. We try to do these about every quarter. So anyway, have a good day. Thanks a lot. Bye.
Thank you. Have a good day, you too.